available on the GeeCON channel soon. I contributed to Jackson Core. I created a project called Log42 Elasticsearch, which I will mention later during one of the slides. And I also have a very fast hobby. Speed matters in a lot of places. Opinions expressed here are mine, not LMAX. Also, a disclaimer: all the technologies that I'm mentioning here were there for a reason or are still there for a reason, and it's not the purpose of this talk to diminish them or harm them in any way. So, what's speed? Speed can be defined as the rate at which someone or something moves, operates, or is able to move or operate. Also known as velocity, quickness, rapidity. Who cares about it? Well, police cares about it, duh. But really, in IT, who cares about it? Well, ideally everyone, right? But speed in various areas is very subjective. For our customers, it is important to go to our website or use our service, and it's important for them to finish their journey as quick as possible. For customer support within our company, it is important to deliver a fix for any sort of issues as fast as possible, since the issue was created until the fix is deployed in production. For the product owner, time to market is important. It's important for the product owner to be sure that our products arrive in production in a timely manner, and they are of certain quality. For developers, it's faster everything. We care about speed ideally we care about speed at any aspect of our work. Usually for us, when we talk about performance and speed in IT, we talk about application performance. But the types of speed I'm going to cover today go well beyond the raw speed of your application, of your code execution. I hope you enjoy it. But first, a bit of context. This is one of the first machines that tried to automate, tried to take some input and process this input into some sort of mechanical process. This is a loom, patented in 1804. It was an improved machine based on inventions of previous generations, previous people that tried to design this kind of machine earlier. In later iterations of various types of automation, we try to improve the speed of processing our punch cards in this case, and try to perform some calculations as fast as possible. This particular machine was patented in 1887, and it reduced the data calculation time from 8 to 2 years. And the person who invented it later was one of the founders of IBM, a company that exists until this day. The speed evolved. Our calculations, automation of calculations, processing of input-outputs, bits of data, was used in a variety of applications. This machine is an evolution of the previous calculus, invented in 1949. Computers, well, digital machines got eventually more complicated, more sophisticated. Technology improved. More inventions came to the market. This is ABC, one of the first vacuum tube-based arithmetic logic units. Moving forward, Colossus in 1944 was the first programmable digital machine. And since then, the evolution of the speed, at the rate at which our computers could process data was ever increasing. A unit of measurement was developed called MIPS in 1977, which was agreed to be a standard standard unit of measurement for any types of further calculations. It became a well-accepted standard in the IT industry. Notice that this scale is logarithmic. The previous graph shows just 20 years, roughly 20, 25 years of data, where the progress was fairly linear. Starting in 1977, the progress became exponential. And the evolution never stopped. Then came the internet. Then came the miniaturization, and it eventually led us to accept the common fact that computers can process data very, very fast. That whatever task we execute at a computer, it will execute it in a blink of an eye before we even realize it. But somehow we got distracted. Maybe we took it for granted. So in the last 20 years, there were multiple hypes that distracted us from the key thing that the most important thing that we are supposed to deliver to our customers: new features, reliable systems. And some of those hypes were very healthy, improved the way we deliver software, improved the way we think, improved the way we design our systems. And in the latest evolution, the biggest latest hype, AI, big data, machine learning, will cause potentially the biggest revolution in the first few decades of this century. And there were positive effects of these hypes. There was a giant improvement in virtualization technologies that affected our operating systems, the way we automate delivery of our services. We started to focus on treating machines like cattle, but also we started to focus on testability, on ways to reproduce whatever conditions happening in prod are always happening on our local host, any staging environment, any machine that we deploy by using Docker or similar container-based technologies. And also, it caused to create some monopolies. It caused some of the vendors, cloud providers like AWS, to generate record growth. If your company can grow at that rate, you're the lucky ones. But there were also negative effects. There were also negative effects. We started to repackage whatever previous technology we had. We started to put abstractions on top of it. This particular picture represents a fashion trend called extreme layering. I had no idea that this kind of thing exists, but hey, we're always learning. The explosion in new technologies also caused CV-driven development. We don't want to work with old technologies anymore. We want to build our CVs, put as many technologies as possible to actually be competitive in the market. But while you're watching this talk, I would like you to think, is this the key to our success? Are there any other qualities that we can have to improve our competitiveness in the markets? And the markets tries to evolve very quickly. The markets, whenever there is a new technology, companies want to jump on it immediately. They know that their competitors probably do the same thing. We want to be we want to be on the markets with the latest and greatest as soon as possible. But it eventually leads to a situation where as Ags mentioned in his previous talk, a product owner or whoever from the business representing, product representing group comes to the team and says, "Hey, we're gonna have a great product." And team says, "Okay, what's the product? No clue. But we're gonna use the 3K, the Kotlin, Kubernetes, and Kafka, because that's what's hyped today." Without any considerations what the product has to do, what is the functionality, what is the value for the customer that we have to provide, what sort of business logic we have to implement. We already know what technologies we are going to use, even though they might be inappropriate for the purpose at best. We started to overuse the word legacy. Whenever you see a blue screen, this is one of the causes of slowness that I observed within the last few years, a decade of my career in IT. So we consider our code legacy very eagerly, but the product is still there. There's no such thing as legacy product unless you really want to retire it from the market, right? What we consider legacy very often is the code that we want to maintain or don't want to maintain. And whenever there is a new technology, there's always this urge to check it out, to implement it in our project as soon as possible, because we have a fear of missing out. We want to learn more. Maybe that's probably the best thing about it. However, whatever we choose to use might hinder the development of features that are so important to our customers. So how can a code survive for more than 3 or 5 years, or whatever the rate of new technology is? Scenario 1, we just say, we need something different. There might be various reasons for that. One of them might be, well, lack of it doesn't have any tests. It works, don't touch it. Any change is perceived as risky because we have zero confidence in in the service that we are changing. We have no confidence that what we just developed is good. And source code, not the most readable in this case. It's difficult to understand, and everyone that wrote it already left the company. And also, there is this unknown tech debt that no one knows how or no one wants to address anymore. Just bounce this machine once a day or every now and then, because it has this memory leak, you know. In scenario 2, the application is well tested. The application is simple. Architecture is simple. Code is simple. Code is efficient. If you would like to replace it, what do you want to replace it with? You can change this application with confidence. You can understand what's going on inside your services quickly, and you have a very good ROI on whatever you invest in hardware or cloud or whatever platform, whatever means to deploy your software you choose. And I would like to focus on this bit first. I identified a very common principle in good software projects. Things that are very important for good teams delivering great products. Make it work, make it nice, and then maybe make it fast. Sometimes you don't need speed immediately. However, if you invert it, modify it slightly. If you make it work first, this is the top priority of your service, then make it fast, like properly, extremely fast, and then make it nice, you're going to find a very surprising thing. If you try to make your application fast, you will make sacrifices. Sometimes the code will not be the most beautiful code in the world, but you're ensuring that this application will last. It will sustain company growth for the next 5, 10, maybe 15 years. You're creating conditions from the very beginning. You're creating conditions that will allow this application to survive for a very long time. Because migrating to anything else just doesn't calculate. Makes no sense. So, how to identify the inefficient code? How many times you found yourselves looking for any sort of performance degradations or just bad code? How many times you actually benchmarked the smallest bits of your algorithm in whatever part of a system? Let's talk about Java for a moment. I'll try to show you a few examples of very common technologies and what did I do to make them at least slightly faster. And I decided to go for loops. For loops, regular good old standard for loops for int I equals 0, blah 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 blah. What I did find in benchmarks that I created is that results are a bit confusing. This is a graph of presenting the number of operations per second over array list. How many times you can iterate over array list of size X, depending on the size of the array. You can see the size of the array at the bottom. How much data you have. Starting at roughly 1,024 elements onwards to the left, the performance difference is not that high. However, if you have some tiny arrays, 16 bytes, 64 bytes, there are differences in ways we can iterate over a simple array list. Turns out that JIT does various weird things that I will not try to explain today because we'll probably run out of time. But I can show you the code. And if you have some immediate ideas, give me a shout. So let's start with ArrayList dummy. ArrayList dummy class that simply creates an array list at the very beginning of its existence, allows you to add some elements and executes various operations, whichever type of loop you prefer. The for each one's very readable, very nice. The for loop, the good old horrible bad looking for loop. I know that this is not really the way we iterate over array lists, but when you look at the results of the benchmarks, you will find some surprises. Size 1's for loop. Maybe this will help. We don't have to access the object size on every execution, on every check. We can do it once. Sounds like a reasonable improvement. And also the ones with maybe local variable and similar, trying to calculate the size once. And another option with just assigning it to a variable and doing a regular for each loop. And the results are surprising. In this particular case, turns out that for loop is actually faster. If you'd like to chat more about it, give me a shout after the presentation. Similar thing happens for arrays. However, in this case, it's inverted. It's the for each loop that's faster for some reason. And the for loop doesn't perform that well. However, even the worst case of iterating over a simple small array is way faster than iterating over an array list. The answer for this is quite easy. There's less code, meaning our CPU doesn't have to do that much work. The overall performance, the overall throughput of this benchmark will be better. So embrace arrays. Before I jump to the last example, let's take a look at Spring Boot. How many of you are using? How many of you use Spring Boot in their companies? Loads of hands. You probably know what I'm going to tell you, because you probably found it as well. So Spring Boot is basically a bunch of factories. Loaded by the service loader, and in order to prepare for this presentation, I created a very non-magical script that simply starts up Spring Boot and immediately kills it. And and on the left, I'm capturing the log, and you can see how long it took to start up your application. Does anyone of you know what is happening during Spring Boot startup? Yes.
What's not happening?
True that. What is not happening during Spring startup? That is a very Satan is probably very much involved in this startup. Let's try to figure out how to optimize it, right? So the reason why Spring Boot startup is so slow, I mean, all right, at least part of it, is it loads a lot of auto configurations, and you can exclude them by just specifying the list of excludes in the Spring Boot application annotation. But do you really want to have this in each and every one of your services? Probably not. There is another way. You can put it in a variable. I believe it's called Spring Startup Exclude or Spring. There was a special name for the property that will do exactly the same work. But there is a third way. Oh, by the way, the size of this property, last time I checked, was 11 kilobytes. If you're happy with having a 11 kilobyte long process line, I mean, of course, this is just a property. You need much more parameters to start up the application. Enjoy. I don't. So what else can we do? Given that Spring uses the Spring Factories file to store anything that's started with a service loader, we can write our own auto-configuration filter. Unfortunately, there is no filter that allows you to say, I only want those auto-configurations to load. There is one that will say, if this class is present, then load it. There is another one saying, if this class, if there are properties for this class, yes, sure, obviously load it. And the exclusion mechanism, which has its pitfalls, right? So I wrote the actually included condition filter, which is a fairly simple class. The actual gist of this class is just these 10 lines. There's probably a very similar piece of code somewhere in the internet, because I'm pretty sure that there are people like me who really like to optimize things and make things fast, and did similar job. Don't worry, most of this code will be available on GitHub, likely this week. So our Spring is currently starting anywhere between 1.1 and 1.2 seconds, roughly 1.2. Okay, so let's try to rebuild it and see if it did it any favors. Kill Spring, go. It should eventually stabilize, but from 1.1, 1.2 seconds, we suddenly dropped to roughly 900 millis, 950. Sometimes we go beyond 1 second. Spring startup is very non-deterministic. Spring Boot startup time is very non-deterministic. But as you can see, we already saved maybe 150, maybe 200 milliseconds, which is not really relevant for the overall application runtime, but it's if you'd like your application to start up faster, that's one way to do that. Interestingly, it took me roughly 2 or 4 hours to develop this whole thing. Okay, let's kill Spring again. Lombok. Who uses Lombok? Okay. For the love of God, I know. So I created another set of benchmarks. Another set of benchmarks that will compare the performance of our beloved equals and hashcode method. Does anyone know what equals and hashcode is? I mean, all right, you do. Do you know what code is generated when you specify this particular annotation? Java P verbose class path targets. Lombok is great. And let's take a look at class I love Lombok. Okay. Whenever you specify this annotation, Lombok will generate a piece of code for you, and inside this block of code, this auto-generated block of code, it will invoke your getters. Fine, does the job. Calculates the hash code in a regular manner. Oh, honorable mention. This will apply only to immutable objects, obviously. I mean, sorry, not in case of Lombok. Let's jump to another iteration of hash code, the IntelliJ generated one, using object hash. If you're wondering what object hash is doing, it's simply multiplying the value of each one of those fields by 31 and returns a value. Nothing really complicated. There you go. I created another class. Where I'm calculating the hash once on creation. And given that most of the benchmarks that I created for this particular purpose are using hash sets or hash maps, various hash-based collections, if you do it once, you don't have to calculate it ever again. You can imagine that Lombok does the calculation every time. Objects hash also doesn't cache anything, so you execute this calculation every time. If you stash your object in the collection and access this multiple times very often, you will notice that beyond 2 or 3 fields, the improvement is quite significant. This also will depend on the size of your array. And here are the results. Notice that in case of very simple hash sets, the performance of hash code generated by Lombok is roughly 57, 55 operations per microsecond. Once you define your hash code, assign your hash code once, calculate it once, it actually speeds up by quite significant margin, 20%. Obviously, we rarely execute it 20 million times a second, but these kind of improvements, they compound on top of each other, right? The speed of your application, responsiveness of the service of your website presented to the customer is a combination of small things. A lot of advice regarding benchmarking, profiling, tries to focus on the biggest bottleneck, and that's perfectly fine. But dealing with biggest bottlenecks is just one side of this problem. If you do multiple small improvements, these effects will compound, will accumulate. Your clients will see that your service is much more responsive. There was a very good talk from Azul about how not to measure performance. Let's say that you have an application that executes, a website that executes 100 calls to your service, tries to load various files, execute many type of requests. If one of those requests has way worse performance, you will hit this negative case very often. The page will load slower, customer will get bored, he will go to the competition. You can measure this. You can measure how your performance improvements affect customer journey. You can use various types of KPI. Usually it's called somewhere around customer conversion rate, customer retention rate. Do whatever. Name it whatever you wish. Your customers will be happier if your service is quick. And by the way, development of this took also roughly 4 hours. Next example has no code. There is no code, but there is a very old tool called GCViewer that can visualize how your garbage collection was behaving. How much memory was there before the garbage collection, and how much memory is there after. It's not the most beautiful tool in the world, but it does the job. This particular application, and yes, there is a nice saw graph. This particular application was given a 64 megabyte heap. It deallocated 60 gigabytes of memory during 2 minutes and 13 seconds lifetime. Application throughput, meaning how much time is spent actually doing actual work versus how much time is spent on GC, was fairly poor. And in just over 2 minutes, we executed 1,700 minor GC collections, inducing a pause. 1.1 second was spent during garbage collection only. Who thinks that this GC is excessive? Fair. It's a rhetorical question. Of course, it's excessive. It's absolutely nuts what this application is doing. But are you wondering what this application is really doing under the hood? Why this application is generating this amount of garbage? So this is a file sender that I recently wrote. In 2 minutes, it sent 55 gigabytes of data to another service, to another process. Roughly half a gigabyte per second. The whole application is garbage-free, apart from tiny little dependency on Netty. And all this allocation comes from the Netty library itself. It is really difficult to fix it. However, I also spent 4 hours to develop a fork And applications send 55 gigabytes of data, allocating only 200 megabytes during its whole life. Throughput increased to almost 100%. Have you noticed one common thing across most of these examples? Any ideas?
We love the third-party libraries.
Yeah, of course we do. Development of each one of those improvements didn't take much time. If you know, I actually know perfectly where to put my hands in. Therefore, for me, maybe it was simply easy, right? However, if you spend following 80-20 rule, if you spend 20% of time, you can usually resolve 80% of your issues with performance, quality, efficiency. If you want to go beyond that, go nuts. But word of warning, it will take way longer to deal with the last 20%, as 80-20 rule claims. So, forking open source was fun. However, you're increasing the risk. Once you start to maintain your own fork, you're lacking context, you're lacking all the tech debts, all the quirks, unfinished features that only maintainer knows about. And if you eventually create a PR, it might get merged. Or maybe because of you lacked context, this particular change was considered by the maintainer many, many times, but it was never implemented because it just covers this very, very tiny corner case that blocks this particular improvement. Obviously, the reasons might vary, but this is just a good example. So, try to write simple code. Simple doesn't mean easy. Complex is easy. It's very easy to write bad code. It's very easy to create a complex system that no one wants to maintain, no one knows how to work with. Simple is very hard. And if you eventually develop anything without searching Google, you'll be happy. You'll be a happier person. You'll have this pride, and you're like, yes, I didn't have to develop, didn't have to search the whole Stack Overflow to find a solution to my problem. And there are problems that only you can solve, that only you know about, that internet will never know, like the domain of your application, what's the roadmap of your application, what is the tech debt, and ultimately, what are the limits when your application breaks, how well it performs. Internet will never tell you that. You have to measure it on your own. You have to write your 10 lines of code without Google. Another massive contributor that slows us down is lack of testing. You have to spend more time to develop any feature because you're constantly debugging, trying to fix the code that you developed quickly, and you don't know whether it works or not until you ship it to production. And sometimes you have to fix it very quickly. Is your fix working? You don't know. You should never assume. You should always measure and always verify whatever piece of code you wrote. Try to test everything. Might seem obvious. All right. There are various levels of tests. Obviously, testing absolutely everything is very, very time-consuming and possibly impossible. Develop just enough tests so that will provide you with enough confidence to change this code. Once you invest time in this process, you will eventually develop a lot of trust in your team from people higher up that constantly doubt the speed of delivery and the way you ship the product. Save yourself some time. Embrace your testers. They are the people that know probably the most about the system within the, sorry, not the system, the business, probably much more than you. We are focused on just if conditions, connections, Dockers, Kafkas, Kubernetes. Testers look at the application from a customer perspective, at least ideally. So we can work together to develop a test suite that will provide them with confidence that the application is tested enough, and will provide you with confidence that you're shipping something that was well tested and will work in production. Try to shorten the feedback cycle, change often. Save yourself some time. Obviously, there are various levels of testing: unit tests, integration, acceptance, performance, various types of performance tests. If you don't know JMH and JC Stress, I highly recommend you Google a bit this time around. And if you like to produce this kind of graph, you will need some kind of test bed. But this graph represents not the speed of your code, but rather speed of your current code in very particular environment. Whenever you change your code, this line should go up or down. You're either improving or degrading performance of some very particular piece of code that you're testing. The environment should be stable, should use exactly the same hardware as production, ideally. I know it sometimes costs a lot of money. However, you can scale it in to cut the costs and get the feedback that will provide you with the efficiency and throughput of your tiny bits of code that will improve the overall customer experience. Ideally, store the results for a long time so you can see the trends. Build yourself a baseline and spot what caused eventual degradation. Meetings. This will be a quick one. Just, yes, impossible, right? There is a way to save a lot of time. Instead of inviting 20 people to the meeting, let's say that your team has a development team has 20 people or 15, and each one of you are tied to the Scrum, and you have to vote. You have to put the number on the complexity that you anticipate. You can use a bit different strategy. While a lot of people during the meeting are not contributing, and it's usually the product owner and lead of the particular feature story are involved. They know what they want for the product. You can have just one more person, 3 people, that is rotating. It can be a tester, it can be a senior, it can be a junior. Juniors have very little exposure to negotiations like that. That's the way they can learn. This way you can focus much better. Instead of addressing 20 people, you can address 3. And upskill people that have no exposure to this kind of process and make them upskill faster. Dependencies on other teams. Sometimes you need help from other team. Sometimes you need some tiny field over there. When things go south, it's not their fault that they haven't added these fields to the API call as you want, because they may have a backlog as long as yours. You can jump to their team for a few hours or days. Get to know their product. Tell them what you need, how important it is to you, and row in the same direction. Because it is likely that their priorities and your priorities are both very important. So share the mindset of trying to row in the same direction. The shore is over there. We just have to get there together. Working alone. Have you ever got stuck trying to solve some problem? How many times you get stuck and you don't ask for help? And how is your feature delivery going? And I can assume that it was if it's some Scrum, then the line is flat, and then there's a very, very nice cliff just 2 days before the end of the sprint. You can solve it quite easily with pair programming. You can pair any 2 people and rotate every day, every 2 days, so that you work together. You learn together. You're not sitting in 2 different corners of your office being unhappy about someone else's code. If you see that someone wrote a bad code, you can just tell them, because you're sitting on the same keyboard, same monitor. You will learn quicker. If it's a senior-junior pair, the junior will learn very, very quickly, helping the team, helping the business, and helping the product. Same with mids. You can pair with testers, develop test suites. Try not to delay the integration, right? This actually applies best for full-stack developers, but let's say that you have a front-end developer that would like to work on some back-end, and you are wondering what sort of techniques this expert front-end developer uses. You can work together, get any path working, integrate very, very quickly, and get feedback on your work. Because the more time you spend perfecting a product, the bigger the risk there is that you're going to be delayed with your feature. Pair programming also allows you to get rid of code reviews, because already 2 people looked at this. Tomorrow there will be other pair looking at the same thing, or at least half of the pair. This way you can start to trust everyone involved in developing the story, development mindset of shipping a well-tested, high-quality code. Deliver with confidence in every single member of your team. The bloated feature set. If you use feature toggles or not, you can ship to production quickly. Once the feature is live, you can start to collect feature metrics, giving you feedback on how your feature is actually used. If it's not used at all after a year or 2, just drop the code. You don't have to execute. Always check for the if condition that's always false, because no one uses it. And if it's some code special case for some obscure case, or maybe some very important customer, make the decision on your own. Usually, less code is better. But as I showed you in the benchmarks earlier, that's not always necessarily true. Try not to copy the wrong patterns. Whenever you decide to start a new project, you can reuse code. You can move over all the bugs, but maybe it's not only about the code. Maybe it's about the methodologies that you used in the previous project, something that you deemed necessary for the new project to succeed. If it doesn't work, you can always go back. You can eliminate things that don't work for you. But if you see something succeed, use it as a template and improve on top of it. All right, quick conclusion. The actual concrete methodology that you use in projects is actually irrelevant. You can GeeCON your way to success. Doesn't know GeeCON? It's a martial arts developed by Bruce Lee, adopting the best elements of a lot of different martial arts to his own style. You can do exactly the same thing. You don't have to follow Scrum to the letter. You can mix Kanban, you can mix XP, you can mix some Scrum elements, you can mix whatever you need. Even in a big organization, you're going to land in some place where you can experiment. You can see if it works. If it doesn't, fine. Change it, try something else. Iterate quickly. And sometimes you just adopt some technologies because everyone else is doing it. But Something that works for Netflix might not necessarily work for you. And at some point, you're going to realize that the whole system is so complicated that you want to simplify it by just getting rid of things that are obsolete. And whether you go for paid tools or decide to write the one on your own, it depends. Depends on the scale of organization, depends on what you need. The possibilities are endless. There is an endless potential in what you can do. There is a potential in each and every one of you to start delivering your products better, starting tomorrow or Monday. And I hope that in the end, you will find that in each and every one of you, at least a part is a farmer. Thank you. It's a bit late for questions, but give me the one or two. Or what are the questions? Oh yeah, there are questions. Do you think that fixes are actually worth it in case you spend 4 hours on a fix that will cut 200 milliseconds from the app startup? Startup time, it will take very long to pay up. I disagree. Every single tiny improvement will pay off eventually, right? Let's say that you have, it probably depends on the scale of your application, on the scale of the service, and how many instances you start, how important it is for you to start up some dying service that just didn't respond to Kubernetes health check. Every single improvement will eventually pay off. If it's 200 milliseconds, it should pay off at the scale of hundreds of services or thousands in your farms. You will go back to liveness very quickly. Forks consume in the middle of for loop. I developed this code quickly. Maybe too quickly, fair enough. And you're right, Yaroslav, this is one of the ways to deal with this, yes. What changes did you make in that library? It's a very particular spot in the frame encoder. Netty decides to allocate a buffer for every message you send using a partially pulled byte buffer allocator. There is no way, this was actually Netty plus Vertex, there is no way to specify which allocator you want to use via Vertex DSL in a way that it will land in this particular encoder. I simply create a fork that allows it. And instead of using the partially pulled allocator that allocates pulled buffer for I/O buffers and unpulled one, which is basically accepting the buffer in your message and writing it further down, and then slayed immediately by garbage collector, you can simply use a pull by buffer. And I hope that nothing breaks. I don't know yet. I need to talk to the maintainer and figure it out. All right. Thank you.